We're going to dive into an idea that sounds kinda scary, but is actually super intuitive, the integral. I want you to forget all the complex formulas you might have seen, because at its heart, integration is just a really clever way of solving a simple problem we see everywhere. How in the world do you measure something with curvy edges?
Here's how we're going to break it down. We'll start with a little visual puzzle I call the curvy area problem. Then we'll check out a brilliant workaround using something simple, rectangles. After that, we'll uncover the integral's secret identity as an antiderivative, learn the shortcut for how to actually do it, and finally, bring it all together to see how these two big ideas are really the same thing. Sound good? Let's jump in.
All right, let's kick things off with the main challenge, the curvy area problem. You know, it all comes down to trying to measure something that our usual math tools they just can't handle it. I mean, really think about it for a second. Finding the area of a square, that's easy, right? Length times width. A triangle? No problem. But what happens when you run into a shape like this, with a weird, flowing, curvy edge? All of a sudden, our simple formulas just don't work anymore.
And this right here, this is the classic calculus problem. We want to find the area of that shaded region. See how it's kind of trapped between the flat bottom axis, two straight sides, but then has that curve on top? There's no simple length times width for that. And solving this exact puzzle is pretty much why integral calculus was invented in the first place.
So how did they figure it out? Well, they used a brilliant workaround. And it all starts by estimating the area with something we do know how to measure really easily, good old rectangles. And honestly, this is where the genius of the whole thing really starts to shine. The main idea is just this. If we can't measure the big, complicated, curvy shape all at once, what if we just chop it up? What if we slice it into a whole bunch of simple shapes that we can measure, like, say, a bunch of rectangles? It's kind of like trying to build a perfect circle out of tiny, square Lego bricks. The more little bricks you use, the smoother and more accurate your circle looks, right?
And you can see that exact idea playing out right here. Look at the picture on the left. With just a few fat rectangles, our estimate is, well, it's pretty clumsy. You've got all those choppy bits sticking out and big gaps missing. But now, look at the right. When we use a ton of super thin rectangles, they start to hug that curve almost perfectly. The total area of all those skinny rectangles gets unbelievably close to the real area.
Now, this whole process of adding up the areas of all those little rectangles actually has a name. It's called a Riemann sum. And here's the absolute key. As we let the number of rectangles, we call it n, approach infinity, basically making them infinitely skinny, the sum of their areas stops being just an approximation. It becomes the exact area under that curve. This whole concept of an infinite sum is really the heart of what we call the definite integral.
Okay, but here's where the story gets a really fascinating twist. It turns out this amazing area-finding tool has a secret identity. It's not just about shapes and geometry. It's actually something way more fundamental about how things change.
And that secret is that an integral is also something called an antiderivative. Now that sounds technical, I know, but the idea is actually really straightforward. Remember how a derivative tells you the rate of change of something, like its speed or its slope? Well, an antiderivative does the exact opposite. It's like someone tells you the rate of change, and you have to figure out, okay, but what was the original thing that was changing at that rate? You're basically working backward.
So here it is in a nutshell. With derivatives, or differentiation, you start with a function and you find its slope, its rate of change. With integrals, or integration, you do the reverse. You start with the rate of change and you work backward to find the original function. One process breaks things down and the other builds them right back up again. They're literally two sides of the very same coin.
Okay, so thinking about an infinite number of impossibly thin rectangles is a super powerful idea, but let's be honest, it's not very practical for actually solving a problem. But here's the good news. Because of that secret connection to antiderivatives, we don't have to. We can go from thinking about infinite slices to just a few simple steps.
And this right here is the key. For a huge number of functions, we can use this basic integration rule, sometimes called the power rule. It's an incredible shortcut that lets us just completely skip over that whole infinite rectangle business. It tells us exactly how to find the antiderivative for any power of x. And that little plus c at the end, that's the constant of integration. We just add it because when you take a derivative, any plain number disappears. So when we go backward, we have to remember that some constant could have been there.
Let's just walk through a really quick example to see how easy this is. Let's say we want to integrate x to the fourth power. Okay, so we follow the rule. First, we add 1 to the exponent, so 4 becomes 5. Simple. Then we divide the whole thing by that new exponent, 5. And last, we just tack on our friendly constant of integration, c. And that's it. We found the integral, and we didn't have to think about a single rectangle. Pretty cool, right?
So let's zoom out for a second and put these two huge ideas together, just to get the full picture of what an integral really is. The two big things to take away are this. First, the integral is the answer to the area problem. It's our tool for finding the precise area of these weird, curvy shapes. And second, the integral is the answer to the reverse problem. It lets us work backward from a rate of change to find the original thing we started with. The fact that these two completely different sounding ideas are actually connected is one of the most beautiful and powerful discoveries in all of mathematics.
And that kind of leaves us with a final thought. This tool, it's not just for finding the area of some abstract shape on a graph, it's used for everything. From calculating the volume of a fuel tank on a rocket ship, to figuring out the total energy used by a city, to even modeling how populations grow. By giving us a way to add up infinite tiny pieces of change, integration lets us precisely measure a world that is always moving, always flowing. So the real question becomes, now that we can measure the irregular, what problems can't we solve?